so let's give you a summary of electron migration and thermal migration. For electron migration, which means that there's a cross effect between the diffusing atoms and the electrons flow through the momentum exchange effect. And we use the effective charge to describe the direction and the amount of atomic flux induced by electrons flow. And electron migration flux it can be counterbalanced by the flux driven by the concentration gradient or the stress gradient. And regarding to the thermal migration, which is a cross effect between the diffusing atoms and the heat flow, we also use the term heat of transport to describe the direction of diffusing atoms and also the exactly amount of the atomic flux driven by this temperature gradient. And thermal migration flux can be counterbalanced by the flux driven by the concentration gradient. Okay, so let's move to the fourth sections entitled capillarity effect. Actually, capillarity effect means actually is the curvature dependent surface chemical potential, which means there's a variation in surface chemical potential due to we have curved materials. And the surface evolution driven by minimization of the surface chemical potential, which means this kind of capillarity effect will lead the surface planization. So as we mentioned before, we are going to have a mass transport under the surface potential gradient, which means there's definitely a surface potential variation on your materials. In most of cases, what we have is instead of a flat surface, we have a curved materials and can be like this. And as you know, the atoms under this surface between the gas and the solid phase have different surface potential. At the convex region, we can the surface potential can express like this, equals to mu A0, means the chemical potential of atom A on the flat surface plus the extra term, and this term actually included the gamma is surface energy, the omega is the average atomic volume, and inside this is kappa 1 plus kappa 2. Kappa is the curvature. Kappa 1 and kappa 2 is which this curvature to describe a curved surface. For example, like this, in order to well describe any curved surface, normally people will use the curvature kappa 1 and kappa 2, which is a reciprocal of a radius, to describe this curved surface. So based on this, back to here, you know the atoms, if it's located at the convex region, like here, the surface potential it can be expressed like this, and this term, because this is positive, positive, and positive, so this term, this surface potential on this convex region is larger than that on the flat surface. When you move the location to the concave region like this, the surface potential expressed like this is mu A0 is the surface potential of atom A on the flat surface minus the extra term. This extra term is the same with this one, is included the surface energy, average atomic volume, and also the two kappa 1 and kappa 2 is a curvature. kappa 1 and kappa 2. And minus the extra term, this term is positive, so you know the surface potential of atom A located at concave region is smaller than that on the flat surface. So here on these materials, we observe there's a surface potential variation happens, right? So because there's a variation in surface potential, and we also observe at the atoms at the convex region has a higher surface potential than that on the concave region. So this surface potential gradient will drive the atomic movement from convex region toward to concave region, like this, JA or JI. Okay, and additionally, some people probably will question about the kappa. Here I use the kappa, the positive kappa to describe the atoms at the convex region, and use the negative kappa to describe that the atoms at concave region. The reason here is here you plus the extra term, right? And this term is positive, so which means the kappa 1 and kappa 2 is positive, right? And at this region actually is the surface potential on the flat surface minus the extra term. If you take this out, you can consider this kappa is negative. So in this way, I will suggest you to remember that the kappa, when you describe the atom at the convex region, you directly use a positive kappa to modify the surface potential term. And if the atoms located at concave region, I would suggest you to use the negative kappa to modify the surface potential term instead of use this one. Okay, so it's easier to remember. Okay, so now you know there's a variation in the surface potential, which means that there's a surface potential gradient which induce this atomic flux from the convex region toward to concave region. And some people probably will ask, yes, the atoms diffuse or move, right, from convex region toward to concave region, but by what kind of a mechanism of this diffusion process? So that would depending on the material system we are talking about. If this materials is the doped metal, and the dopants will locate at interstitial site, then under these conditions, the interstitials will move or diffuse from the convex region toward to concave region through interstitial size. But if the material system we talk about is a pure metal, and the diffusion mechanism of this kind of pure metal probably is vacancy mediated diffusion process. Under this case, the atoms at the substitutional site is going to diffuse or exchange the location with surrounding or nearby vacancies, right? So this will be substitutional atoms. And under this kind of pure material system, you also can you also can use the vacancy flux to describe this kind of vacancy mediated diffusion mechanism, right? So we got the vacancy flux from the concave region to the convex region, right? Okay, that will be the case for vacancy mediated material. Okay, so the driving force here will be the gradient of diffusion potential along the interface. So now you have some ideas how the atoms transport under the surface potential gradient, right? So next, I'm going to show you how to formulate the surface chemical potential of the atoms on the flat surface. We'll start from the flat surface, okay? So how to calculate or formulate the surface chemical potential on the flat surface? So in the beginning, what kind of material we have here is we have a pure A materials. So in this kind of material system, we only have two components. One is atom A and the other one will be the vacancy. So now we consider this material with Na atoms and Nv vacancies. And as you know, the numbers of atoms is much larger than the numbers of vacancy by at least 3 orders, right? At constant temperature and no electrical field. At constant temperature imply that there's no thermal migration, and no electrical field implying that there's no electron migration in these systems. So here, the purpose here is we want to show you how to get the surface chemical potential of atom A. So based on the definition, you need to know the total Gibbs free energy. Then you take the first deviated with Na, then you got the mu A, right? So first of all, you need to formulate the total Gibbs free energy of the system will be expressed like Na times mu A0. Na is the numbers of atom A times the atomic free energy in the vacancy-free materials mu A0, plus Nv, the numbers of vacancy times the vacancy formation energy. And as you know, inside this material, the atoms and vacancy mixed well together. So this term actually is due to the mix between the mixing between the atoms and the vacancy. So you got the KT log XA and NV log XV, right? Okay, so now you got this results, right? So we directly take this Gibbs free energy and partial with Na, so you only have this term left and this term. So we can do the approximation, becomes like a mu A0 plus KT log this term XA. And as you know, the Na is much larger than Nv, so we delete this Nv. So what you have here is you have KT log 1. Log 1 actually is 0. So here we have is the chemical potential of atom A on the flat surface is equal or approximately to mu A0 is a free energy of atom A in vacancy-free materials. And then we want to know the chemical potential of vacancy. So also we take the Gibbs free energy partial with the Nv. So we only have this term left and this term. So can express like a vacancy formation energy plus KT log XV. So what you have is you can use the XV to substitute this term. So we got the mu V equals to vacancy formation energy plus the KT log XV. So based on this term, you know the chemical potential vacancy is related, dependent with the atomic fraction vacancy, right? Because the vacant means that the vacancy, the concentration of vacancy will change the vacancy, chemical potential vacancy. And next, I'm going to give you a very important assumption. Here is we assume it is at the local equilibrium condition on the surface. So under this situation, we assume the mu V at the equilibrium conditions equals to 0. So based on this, you got the equilibrium condition, you got the 0 here. So the reason for this kind of assumption is due to, as you know, we don't really have a vacancy flux on the surface or inside our materials, right? Because the vacancies will usually were always trapped into the crystal imperfection size, so we cannot really visualize the vacancy flux flow through our materials. So under this situation, vacancy will trap in crystal imperfection side, including the dislocation, grain boundary, and so on. Under this situation, we also can assume there's no flux be trapped, right? So the chemical potential of vacancies can consider uniform. So under this situation, we can directly assume that uniform, right? The chemical potential vacancy are the same everywhere. So under this situation, we directly assign them equals to 0. So under this situation, you can get the atomic fraction of vacancy in resistance. So you move the Gibbs energy, formation energy here, then you can get the XV expressed like the exponential minus vacancy formation energy divided by KT. This is the atomic fraction of vacancy on the flat surface. And in order to get this one, we made this important assumption here, so we can have this results. So based on this result, some people are very familiar with this equation, right? So as you know, when you increase the working temperature, environment temperature, the vacancy concentration increase in the meantime, right? So based on this, we know the vacancy formation energy is dependent on the temperature and also the vacancy formation energy. But here, the material we talk about, or atoms we talk about, actually is on the flat surface, right? But in the capillarity effect, actually, the materials we have with a curved surface. So based on this, I'm going to ask you, if I want to answer the atomic fraction vacancy on the curved surface, which parameters or which term need to be modified? Is the temperature? No. Yes, it is a vacancy formation energy. For sure, you need the vacancy formation energy on the flat surface is different with that on the curved surface. So we need to modify this term. And how to do that? So you can image that we ended some vacancies on the curved surface or on the flat surface. We need to perform some extra work to push or put the vacancies on the curved surface, right? So that means we need to do some work on that. So in order to quantitatively know how to modify this vacancy formation energy, so let's move forward. We need to know how much work we need to perform to put some vacancies on the surface. So let's take this as an example. What we have here is we have a sphere, you can see like a ball-like structure, and with the radius of r, and then we try to end it a vacancy, or some people probably can consider as the lattice point. It's an empty lattice point into this crystal at the convex region, and this convex region with the curvature kappa. And kappa here equals to kappa 1 plus kappa 2. And in this case, it is a ball-like structure, a spheroid or sphere structure. So the radius is r, capital R, and the kappa 1 will be the 1 over r plus 1 over r equals to 2 over r. Okay? And due to we ended empty lattice point or a vacancy on this crystal, you can expect the crystal expand by delta V, which is average atomic volume or average vacancy volume omega V actually is the same as omega A, right? So average atomic volume, and also accompanied with an increased surface area with delta A. So based on this, we know the surface work is increased by what? Will be increased by gamma surface energy times the delta A. Delta A is the increased surface area due to due to addition of this vacancy. So this is the extra work we need to perform, right? And also will be the extra term we need to put this back to the vacancy formation energy. So gamma is surface energy is easy to check from the literature, but what about the delta A is the increased surface area? So what's this? So in order to answer these questions, we need to start from delta A will be equals to 8 pi r dr or delta r. And the delta V can be expressed as 4 pi r squared dr. The reason here actually is easy, right? I believe you know, but let me write something. Okay. So A actually is 4 pi r squared. So if you partial with r, you got take the first deviated respect to r, though you got the 8 pi r dr. And v actually is 4 divided by 3 pi r 2, 3. So you take the first deviated with respect to r, so you got the 4 pi r squared dr, right? Okay, so now you got this one, right? So when we try to use the delta A divided by delta V, what we have is we delete this term pi r and this 2, so you got a 2 divided by r. 2 divided by r is, in this case, will be equals to kappa. So we know delta A can equals to kappa times delta V. Delta V here is the expansion of this crystal after ended the vacancy, right? So it's the volume of the vacancy is omega V. So delta A can express equals to kappa omega V. So we substitute this to here. So we got the gamma kappa omega V, right? So this is the extra work we need to perform. And so based on this, in this case, kappa actually is equals to 2 over r, right? Okay, so now you know we need to additionally perform this extra work on this material. Then we can have so this will be the extra term. We need to modify the vacancy formation energy, right? So it will be like a gamma kappa omega V. So based on this, we put this extra modified term, extra work here. So we got the atomic fraction vacancy vacancy fraction at the equilibrium condition expressed like the exponential minus vacancy formation energy plus the extra work term. Is the extra work will be the gamma kappa omega V. Some people instead of using this express like this, some people will express like this will be the vacancy concentration will be of the kappa is dependent with the curvature of the kappa expressed like this, and this is CV equilibrium 0. Kappa 0 means on the flat surface, right? So you ended extra term is this term. So either way is okay to express like this one. Or some people, instead of this concentration part, some people divide it and become the XV is the same idea. Okay, so this is and if you just divide this equation by this equation, then you will get this results. Okay, so it's similar because you just divide this, then equals to this, divided by this, and equals to this term. Okay, so now you know the atomic, the vacancy fraction on the curve surface can be expressed like this, or vacancy concentration will be expressed, will be dependent with the curvature. But this is a vacancy point of view, right? Some people will want to move to the atom's point of view. So how about if we ended an atom in the crystal, and how to modify the potential part? So the extra work can also be expressed like this, and we use the omega A, the average atomic volume, to substitute omega V. But if we talk about the same materials, omega A actually is equals to omega V, right? Okay, so when you try to write down the surface chemical potential, will be because how to write this down, the surface chemical potential based on the network constraint. If you only have two components, one is atoms and the other is a vacancy, and NC can be equals to vacancy. So the potential will be mu A minus mu NC, right? So here is mu V. And we assume mu V equals to 0, and mu A here, we need to use the mu A0 plus extra term. So you got mu A0 plus gamma kappa omega A. So this is the surface chemical potential of atom A on the curve surface. And when you try to write down the surface chemical potential on the convex region, don't forget the gamma is positive, so you got the mu A0 plus gamma kappa omega A. If that is a concave region, I will suggest you to use a negative to represent the kappa, so it will be mu A0 minus gamma kappa omega A, so you got this results. Okay, so now you have a surface chemical potential on the convex region and concave region. So the driving force will be take the potential minus potential gradient. So will be usually this is higher potential, lower potential. So the atoms will be moved to the concave region, right? So use this term to minus this term and take the gradient and minus and negative. And also gamma is a constant, omega is constant, so the gradient part will be directly performed on the kappa. And you take the minus here, so be this one minus this one, and you got the minus. Some people probably actually some people ask me about why we always put a minus electrical potential gradient and minus potential gradient minus, due to the potential part, the atoms move from the high potential to low potential. So the way we calculate the surface will be use a low potential to minus the high potential, and this will be a negative term. So we put a negative, extra negative to negative become positive, so the driving force will be positive. So that's the reason why for the driving force we always put a negative something to represent this. Okay, so this is for atom, the driving force for atoms. But if the material we talk about is a pure metal, so you are interested to calculate the atomic flux by measuring the vacancy flux. So the vacancy flux will be the same value but upside sign, okay, for the vacancy. Okay, so now you know how to formulate the surface chemical potential of atom, of your interesting atom on the curved surface, no matter it's on the atom's point of view or vacancy point of view. Now we give you an example here. The example here is a narrow scale Kirkendall effect. Actually, narrow scale Kirkendall effect, we talk about this in lecture in previous slide, right? we tell you how to use this narrow scale Kirkendall effect to synthesize the hollow ball or hollow tube structures. So let's talk this. Let's try to link this with the capillarity effect. Okay, so in the beginning, what we have is we have a core A, share B is this kind of co-share structure. And as we know, the flux of JA is larger than JB, so JA toward to outside and JB will be toward to inside. But JA larger than JB in order to achieve the net flux equals to 0. So we know there's a vacancy flux to move inside vacancy flux, right? So the question here is the direction of vacancy flux. So in the beginning, when you try to heat these materials up and allow the diffusions happen, so the first atomic movement will be occurring due to the interdiffusion between this co-share structure. So will be the Kirkendall effect. So the vacancy will move toward to inside, and as you know, there's a vacancy will accumulate and observe in material A. And after a while, the diffusions continues happen, so you will have this kind of because the void in the beginning void is small, right? And small void will aggregate and form a large void. So the void will get larger and larger, and the outside portion we will get the AB alloy, which means the concentration of atom A and B will be uniform to form this AB structures. And inside we will find a void form here. So this will be the AB alloy with a hollow structure, and the inner radius will be Ri, and the outer radius will be Re. But under this situation, if you still heat these materials up and allow diffusions happen, then next, what happened next? Under this situation, there's no concentration variation of atom A and B, so no chemical potential gradient. We didn't apply the electrical field, so there's no EM. The temperature everywhere are the same, so no EM, no TM, right? So regarding to the surface potential, are they the same? No, right? Because you see the convex region and concave region. So there's a surface potential difference on these materials, right? So if you continue heating materials up, and the capillarity effect is going to take over or dominate the following parts. So capillarity effect tell you the atoms at the convex region will move toward to concave region. So there's atomic flux toward to the center. So that implies that this hollow structure, this ball-like structure is going to shrink. Means the Re is going to shrink. Okay, and this is atoms point of view, but if you want to use the vacancy point of view, it's also okay to explain this kind of shrink. Based on the concentration vacancy of kappa, then you know the kappa on this concave region is negative, so you got an exponential positive term. This term means that the vacancy concentration at the inner surface will be larger than outer surface. The outer surface, the kappa is positive, so you got exponential minus positive term, so it's small, right? So the CV here is larger than CV on the inner surface is larger than that on the outer surface. So there's a vacancy flux move outside. Actually, it's the same idea with you got observe. You say that the atomic flux move inside, right? It's a same value but upside direction. So the vacancy flux moved outside, which means what? This void, the diameter of this void will get smaller. So this implies that this horrible is going to shrink. The same thing, right? Just different point of view is either you want to use the Aiton's point of view or vacancy point of view. So based on the second step, the Keck-Kondo effect capillarity effect dominates, so you can observe the vacancy flux from inner to the outer. Okay, so let's give you two examples before we end these sections. Okay, the first example is we consider we have a cold shell wire. Don't forget this is wire, and made of core A and shell B. And A and B can form a complete solid solution, means that AB can be an AB alloy after annealing at high temperature. And the intrinsic diffusivity of A is larger than B, implying that JA is larger than JB with a dissimilar flux, right? So it will, when interdiffusion happens, there's a Keck-Kondo effect will happens, right? So describe how the AB composite wire morphology evolution after annealing at temperature for 4 hours. So now we hope you can draw the morphology of this wire. So if the size of this wire is hundreds of micrometer, tens of nanometer, or 1 to 2 nanometer, explain your reasoning in details. So due to A larger than B, and when the diameter of this wire is hundreds of micrometer, so hundreds of micrometer, if you have some idea about the diffusion length, we can use the square root of dt or 4dt, right, to estimate the diffusion. Square root, 4dt or dt to estimate the diffusion length, right? It turns out the diffusion length during these 4 hours is play important role to answer these questions. So I give you some orders. Diffusivity in most of cases will be around 10 to, depending on different materials, but order can be 10 to minus 18 meters square per second is around this value. And 4 hours you use the 4 hours to substitute this time. 4 hours times 16 minutes times 16 seconds. So you substitute this one, you will get the diffusion length probably in this kind of case will be around 100 or around 75 nanometer. You can consider around like 100 nanometers. So based on the material what we have here is in the hundreds of micrometers, so it's 100 nanometer diffusion. So this green stuff is around 100 nanometer. And you can, for sure, you can observe some void form in material A. This is for answer for the question A. But if it's 10 nanometer, you can consider almost is already formed the AB solid solution, AB alloy, and you can observe the void form or the hollow structure will be the AB alloy with a hollow structure. But some people probably will struggling. Is that possible to still have some pure A and B here? Yes, probably. If you want, you can draw like that. But major component will be the AB alloy in this case, okay? And if the diameter is down to 1 to 2 nanometers, what happened? Because the diffusion length is 75 nanometers, so roughly like around like a 10 minutes, it already formed a solid solution, solid solution like this, right? And the rest of time, like around 3 hours or more, the capillarity effect will be dominant. So will be first is Kirkcondall effect. And because the diameter is too small, so most of time will spend on capillarity effect. So this structure is going to shrink, right? So the size will decrease doing this tube shrink. Okay, so this is the example 1. And the other example will be this one. Example 2 is we consider we have a metal ball, and the inner radius is 4 nanometer, and the outer radius will be 6 nanometer. So this is a metal ball. So please calculate the equilibrium vacancy concentration at the inner and outer surface, respectively. Okay, so based on this, you need to calculate the vacancy concentration. And based on previous slide, the atomic vacancy fraction of kappa can be expressed like this, right? And this is the vacancy fraction. So don't forget, finally you need to convert it to vacancy concentration by dividing by average atomic volume. Okay, so based on this equation, you just put all the parameters in. So this is for the inner surface, and this is for outer surface. We just put all the information. The vacancy formation energy will be 0.92 EV. So 1 EV is for 1.610 times 10 to minus 18 joule. And extra term is a gamma, kappa, omega. Don't forget the gamma for the inner, you put a negative. And the kappa is, for this is ball, so it's 2 divided by radius, so it will be 4 times 10 to minus 9. For the outer surface, so the kappa will be positive, and also 2 divided by radius. And the rest of part, just put all the information inside here. But this is the vacancy fraction, right? So I'm interested in is you need to answer the vacancy concentration. So divided by the omega, then you got the CV inner on the inner surface and the CV on the outer surface. And based on this, let's check. This is minus extra term, and this term is this term minus extra term, this term is this term plus this term. So this is this term much larger than this term, and you put a minus larger one. So for sure, inner XV is larger than XV outer, right? Because this minus larger one will be smaller. So based on this, the atomic vacancy fraction on the inner surface is larger than that on the outer surface. So we got the vacancy flux flow from the inner surface toward to outer surface. So this is vacancy point of view. So you also can explain this phenomena by atomic flux, point of view. So there will be atomic flux flow inside. So from the outer to the inner. So this narrow tube is going to shrink, or narrow ball is going to shrink. Help me to correct this term. Okay, so next, can you try to formulate the vacancy flux? Vacancy flux actually expressed like can be get by mobility, concentration vacancy, and the driving force. So what's the driving force here? Will be the gamma, omega, kappa, V gradient, right? So we mentioned this before. So the you can put the parameters inside. And regarding to vacancy concentration, we know there's a variation on the vacancy concentration. So for this term, we just take the average on the vacancy on the CV on the inner surface and CV on the outer surface. Take the average for this one. gamma, omega, and the kappa gradient. Gradient actually is kappa gradient, so the vacancy flux is flow like this way. So use the positive kappa minus negative kappa, and divided by the gradient will be the length for this region. So it's 6 minus 4. So this is the vacancy flux. So actually, as I mentioned in class, some people probably will ask, can I use the minus diffusivity concentration gradient to calculate the JV? Can we do that? Because the reason for that is diffusivity. We know, right? Diffusivity is here. Concentration gradient, you got a concentration gradient. Can we do that? But my answer probably would be you cannot do that, because minus diffusivity concentration gradient, vacancy concentration gradient, don't forget the XV. How we get the XV? We assume what? We assume mu V equals to constant. What means mu V equals to constant? Means there's the chemical potential vacancy are uniform everywhere in these materials, right? You already assume mu V equals to constant. There's no variation of vacancy, chemical potential vacancy. So no chemical potential variation. So no. So you cannot use the minus diffusivity concentration gradient. Okay, because UV chemical potential vacancy already be the same. So the vacancy cannot, everywhere chemical potential are the same. So there's no vacancy flux. So you cannot directly use the minus diffusivity concentration vacancy to solve this, to answer these questions. Okay, so you cannot do that. You need to use the you need to use the driving force capillarity effect to answer these questions. Okay, so